Dear students, already we have studied regarding the solutions of gases in liquids as well as liquids in liquids. The remaining is the solutions of solids in liquids. What is the difference between the solid solute and a liquid solute? Now, if you keep water or any other liquid in a vessel, slowly the molecules will be going from the liquid phase to the vapor phase. If you keep sugar in a vessel, will the molecules of sugar go from the solid state to the vapor phase? No. We say sugar is a non-volatile solute. Non-volatile means it will not be becoming a vapor under normal conditions. Other examples are sodium chloride, glucose, urea, benzoic acid, etc. Now let us see what happens to the vapor pressure of the solvent when a non-volatile solute is dissolved in it. You can see in this video, molecules of liquid are going to the vapor phase. What happens when a non-volatile solute is added to this? You can see the number of molecules escaping to the vapor phase decreases. Why is it so? Look at this figure. The solid molecules are represented by blue color. You can see, for example, 6 molecules go up as vapors. In the second beaker, we have a solution obtained by adding a non-volatile solute. Non-volatile solute molecule is represented by red color. ഒരു റോട്ടിൽ ഒരു വണ്ടി പെട്ടെന്ന് നിന്നുപോയാൽ എന്ത് സംഭവിക്കും? ബാക്കിയുള്ള വണ്ടികൾക്ക് മുന്നോട്ട് പോകാൻ കഴിയാതിരിക്കുകയും അവിടെ ഒരു ബ്ലോക്ക് ഉണ്ടാവുകയും ചെയ്യും. അതേപോലെ non-volatile solids in the solution will prevent some of the liquid molecules from escaping out to the vapor phase. What will be the result of this change? The vapor pressure of the liquid will come down, or a solution always will have a vapor pressure less than that of the pure solvent. We have studied one law for liquid solutions, namely the Raoults law. And when the solution is very dilute, we are considering here only dilute solutions, the solution is considered almost ideal, and we can apply Raoults law to this solution also. From Raoults law, we have P equal to x1 P01 plus x2 P02. Here, since the solute is non-volatile, P02 will be 0, and the second term in the equation will disappear, and the equation becomes the total pressure of the solution. P will be equal to x1 P01. And x1 is the mole fraction of the solvent, P01 is the mole fraction, P01 is the vapor pressure of the pure solvent. Since x1 value will be less than 1, P will be always less than P01. That is, vapor pressure of the solution will be always less than vapor pressure of the pure solvent. ഇനി വരാൻ പോകുന്ന ഡിസ്കഷനിൽ വളരെ പ്രധാനപ്പെട്ട ഒരു പോയിന്റ് ആണിത്, ഓർത്തു വെക്കുക. അപ്പോൾ ഒരു സൊല്യൂഷന്റെ വേപ്പർ പ്രഷർ എപ്പോഴും സോൾവെന്റിന്റെ വേപ്പർ പ്രഷറിനെക്കാട്ടും കുറവായിരിക്കും. When concentration increases, vapor pressure goes on decreasing. So, addition of a non-volatile solute to a solvent brings changes in the vapor pressure and also properties associated with vapor pressure. These properties we are studying under a new heading, namely the colligative properties. നമ്മളിപ്പോൾ ഒരു ഷോപ്പിൽ പോയിട്ട് കുറേ സാധനങ്ങൾ വാങ്ങുമ്പോൾ കടക്കാരൻ ബില്ലിടുന്നത് സാധനം എണ്ണിയിട്ടാണോ അതോ സാധനങ്ങളെ നോക്കിയിട്ടാണോ? തീർച്ചയായും സാധനം നോക്കി തന്നെ വില ഇടുക. കാരണം ഓരോ സാധനത്തിനും ഓരോ വിലയായിരിക്കും. പക്ഷെ നമ്മളൊരു ഷോപ്പ് പോകുന്നു, അവിടെ ഒരു ബോർഡ് ഉണ്ട്, ഏതെടുത്താലും 20 രൂപ. അപ്പൊ അങ്ങനെയുള്ള ഷോപ്പില് ഷോപ്പ് കീപ്പർ സാധനത്തിന് എണ്ണിയാൽ മാത്രം മതി. കാരണം എത്ര സാധനം ഉണ്ടോ അതിനെ 20 കൊണ്ട് മൾട്ടിപ്ലൈ ചെയ്താൽ അതിന്റെ മൊത്തം വില കിട്ടും. അപ്പൊ അതേപോലെ സൊല്യൂഷന്റെ പ്രോപ്പർട്ടികൾ എല്ലാം ഒരേപോലെയാണോ? അല്ല, സൊല്യൂട്ടിനനുസരിച്ച് മാറിക്കൊണ്ടിരിക്കും. ഇപ്പൊ ഷുഗർ സൊല്യൂഷൻ ആൻഡ് സോൾട്ട് സൊല്യൂഷൻ വിൽ ഹാവ് ഡിഫറെന്റ് ടേസ്റ്റ്. Sugar solution and copper sulfate solution will have different color because color and taste depend upon the solute. Oh, what about colligative properties? These properties will not depend upon the solute nature. They depend only on the molar concentration of the solute. So how will you define colligative properties? Colligative properties are properties that depend only on the molar concentration of solute particles present in the solution and not on their nature. അപ്പോൾ രണ്ട് സൊല്യൂഷന്റെ മോളാർ കോൺസെൻട്രേഷൻ ഈക്വൽ ആണെങ്കിൽ അതിന്റെ കോളിഗേറ്റീവ് പ്രോപ്പർട്ടിയും ഈക്വൽ ആയിരിക്കും. 1 molar sugar solution and 1 molar urea solution will have the same colligative property. Remember, the concentration should be in number of moles. Percentage ആയാലും പറ്റൂല. ഇപ്പോൾ 1% ഷുഗർ സൊല്യൂഷന്റെ കോളിഗേറ്റീവ് പ്രോപ്പർട്ടിയും 1% യൂറിയ സൊല്യൂഷന്റെ കോളിഗേറ്റീവ് പ്രോപ്പർട്ടിയും ഈക്വൽ ആവില്ല. സോ കോളിഗേറ്റീവ് പ്രോപ്പർട്ടി ഈക്വൽ ആവണമെങ്കിൽ കണ്ടീഷൻ എന്താണെന്ന് വെച്ചാൽ അവയുടെ മോളാർ കോൺസെൻട്രേഷൻ തുല്യമായിരിക്കണം. സോ ദിസ് ടൈപ്പ് ഓഫ് പ്രോപ്പർട്ടീസ് ആർ കോൾഡ് colligative properties. And in this chapter you are studying 4 colligative properties. One is relative lowering of vapor pressure. Another is elevation of boiling point. Then depression of freezing point. And last one is the osmotic pressure. Now let us see one by one these properties. First one is the relative lowering of vapor pressure. Just now we have seen addition of a non-volatile solute will lower the vapor pressure of the solvent, or solution will have a vapor pressure less than that of the pure solvent. This decrease in vapor pressure is called lowering of vapor pressure. The ratio of lowering of vapor pressure to the vapor pressure of the pure component is called the relative lowering of vapor pressure. If P01 is the vapor pressure of the pure solvent and P is the vapor pressure of the solution, then P01 minus P will give the lowering of vapor pressure, and the P01 minus P by P01 will give you the relative lowering of vapor pressure. The Raoults law that you have studied already for liquid-liquid solution is slightly modified for solutions of solids in liquids. I think you know why. Because liquid-liquid solution, both will have vapor pressures. In solid-liquid solution, solid will not have vapor pressure, only liquid will have a vapor pressure. Accordingly, you have a new definition for Raoults law. It is, in a solution containing a non-volatile solute, the relative lowering of vapor pressure is equal to the mole fraction of the solute. I repeat, for a solution containing a non-volatile solute, the relative lowering of vapor pressure is equal to the mole fraction of the solute. Just now we have seen what is relative lowering of vapor pressure. It is P01 minus P by P01, or P01 minus P we can write as delta P also. So delta P by P01 is equal to X2, which is the mole fraction of the solute. So this is the Raoults law applied to solutions of solids in liquids. Now let us see how this law is derived from the law that we have already studied. According to the equation that we have already studied, vapor pressure of a solution is given by P equal to x1 P01 plus x2 P02. Since solute is non-volatile, P02 will be 0 and second part will disappear from the equation, and the vapor pressure of the solution P will be equal to x1 P01. In this equation, we replace x1 with 1 minus x2. Then we will get P equal to 1 minus x2 into P01. Removing the brackets, it will be P01 minus x2 P01. Rearranging, we get P01 minus P equal to x2 P01, or P01 minus P by P01 is equal to x2, the mole fraction of the solute. Now let us see how this relative lowering measurement is used for calculation of molar mass of the solute. Now we have P0 minus P by P01 is equal to x2. But what is x2? x2 is the mole fraction. It is equal to N2 by N1 plus N2, where N1 is the number of moles of the solvent and N2 is the number of moles of the solute. So here in the denominator we have N1 plus N2. Now for a dilute solution, number of moles of the solute N2 will be very small when compared with N1. So in the denominator we are neglecting N2, and this equation becomes delta P by P01 is equal to N2 by N1. What is number of moles? This is equal to mass by molar mass. Substituting, we will be getting delta P by P01 equal to W2 by M2 divided by W1 by M1. Or finally, we will be getting delta P by P01 equal to W2 by M2 into M1 by W1. Here we can see the relative lowering of vapor pressure is inversely proportional to the molar mass of the solute M2. And this equation can be used for calculating the molar mass of non-volatile solutes. Now, let us do some problems involving the relative lowering of vapor pressure. Now look at these problems. Calculate the vapor pressure of a solution consisting of 3 moles of a non-volatile solute dissolved in 15 moles of water at 25 degrees Celsius. Vapor pressure of pure water at this temperature is given as 23.8 torr. Torr is the unit of pressure, which is same as millimeters of mercury. Now let us list the data given. The first data is 3 moles. 3 moles is the number of moles of the solute, which is represented by N2. So N2 is equal to 3 moles. 15 is the number of moles of the solvent, water, represented by N1. So N1 is equal to 15 moles. Then 23.8 is the vapor pressure of pure water, represented by P01. So P01 is 23.8 torr. And you are asked to calculate P, the vapor pressure of the solution. So substitute these values in the equation P equal to x1 P01. So this will be equal to x1 is mole fraction of the solvent, number of moles of the solvent divided by the total number of moles. That is 15 by 18 into 23.8 gives you 19.83 torr. So 19.83 torr is the vapor pressure of the solution. One more problem. Vapor pressure of pure water at 298 Kelvin is 23.8 millimeters. 50 gram of a non-volatile solute is dissolved in 850 ml of water the solution has a vapor pressure of 23.4 millimeters of mercury. Calculate molar mass of the solute and the relative lowering of vapor pressure. Here again, make a list of the data given. So P01 is given as 23.8 torrs. Weight of solute W2 is 50 grams. Weight of solvent W1 is 850 grams. Pressure of the solution P is equal to 23.4 millimeters of mercury. Molar mass of solvent water M1 is 18. So we have relative lowering P01 minus P by P01 equal to 23.8 minus 23.4 by 23.8 gives you the mole fraction as 0.017. So 0.017 is the relative lowering of vapor pressure. Now let us calculate the molar mass. We have the equation delta P by P01 equal to W2 by M2 into M1 by W1. So accordingly we have 0.017 will be equal to 50 into 18 by M2 into 850. Rearrangement gives M2 is equal to 50 into 18 divided by 0.017 into 850 and the answer will be 62.3. So that is regarding the relative lowering of vapor pressure. Now we will be passing over to the elevation of boiling point.